Look at anything around you right now. The cup on your desk, the air in the room, your own body. Every one of them is, in a very literal physical sense, running down. So is the universe that contains them, and physicists can describe roughly how that ends. This is not a story about an explosion or a single violent afternoon. It is quieter than that, and in some ways stranger. It is a story about a rule that never once takes a day off. Start with the rule itself. Physicists call it the second law of thermodynamics, and Boston University's own physics department states the plain version of it in one sentence: the level of disorder in the universe is steadily increasing. Systems tend to move from ordered behavior toward more random behavior. Put another way, on the university's own physics course page, the total entropy of the universe is continually increasing. NASA's Glenn Research Center defines the quantity itself in narrower, technical terms. Entropy changes according to how much heat moves through a system divided by its temperature, and for any real process, the kind that cannot simply run backward, the combined entropy of a system and everything around it has to increase. It never decreases. That is the entire engine behind everything you are about to hear. Not a force pulling things apart. A one-way arrow that governs coffee going cold, ice melting, and, at the largest scale anyone has ever tried to describe, the universe itself. So follow that arrow outward, because right now, the universe is not just sitting still while entropy quietly climbs. It is expanding, and the expansion itself is speeding up. According to NASA, roughly 9 billion years after the universe began, its expansion started to accelerate, driven by something scientists have never directly observed and named only for what it does: dark energy. NASA's own estimate puts dark energy at somewhere between about 68 and 70% of everything in the universe, more than all matter, ordinary and dark, put together. An invisible majority, quietly stepping on the accelerator of the cosmos. Here is the honest, uncomfortable part. Nobody knows what dark energy actually is, and NASA is direct about what that means for any prediction of how this all ends. The space agency lays out 3 real scenarios, side by side, without picking a favorite. If dark energy behaves exactly the way Einstein's own equations describe it, a constant, unchanging pressure, the universe simply continues expanding at a steady clip, forever. If dark energy turns out to be stronger than that prediction, the outcome is far more violent, a scenario NASA calls the Big Rip, in which the universe is torn apart so completely that eventually galaxies, then stars, then planets, and finally atoms themselves come apart. And if dark energy instead fades and eventually flips in force, gravity could win back control entirely, pulling everything back together into what NASA calls a big crunch, the universe imploding the way it once expanded. 3 real doors. Nobody currently knows for certain which one we are walking toward. But the leading picture, the one most consistent with 2 decades of observation, points toward the calm one: continued expansion, forever, growing colder and emptier by the century. That is the scenario this episode is actually about, because it is the one where entropy gets to finish what it started, uninterrupted, for a span of time that makes every number you have heard on this channel before look almost modest. Physicists even have a name for the stages of that long decline. In 1997, 2 astrophysicists, Fred Adams and Gregory Laughlin, published a paper in the journal Reviews of Modern Physics called A Dying Universe, and in it they lay out, in their own words, the evolution of planets, stars, stellar populations, galaxies, and the universe itself over timescales which greatly exceed the current age of the universe. They broke that future into distinct eras, each one longer and stranger than the last. Right now, you are living inside what they call the Stelliferous Era, the age of shining stars, the only era in the entire framework where anything like a sunrise, a planet, or a person watching this video is even possible. Every galaxy you have ever seen a photograph of, every star that has ever been named, belongs to this one narrow window. Eventually, and this is a genuinely long eventually, that window closes. Stars stop forming as the raw material for building them runs low. The ones already burning finish their fuel one by one, and the universe settles into what Adams and Laughlin call the Degenerate Era, a stretch of time dominated not by living stars but by their leftovers, the same kind of stellar corpses this channel has already visited up close. You might reasonably ask how anyone could claim to know what happens after that, on time scales this absurd. Part of the answer is that physicists do not just speculate freely. They test what they can, even when the test takes decades and only tells you what is not true yet. Consider the proton, the particle sitting at the center of every atom in your body right now. Most physics assumes protons are permanently stable. Some deeper theories, ones that try to unify the forces of nature, predict that protons might not be, that over a long enough stretch of time, a proton could quietly fall apart. Nobody has ever caught one doing it. Under a tank holding tens of thousands of tons of ultra-pure water, built specifically to watch for the faint flash of light a decaying proton would produce. It has watched for years. In a paper published in the journal Physical Review Letters, the collaboration reported finding no such event, and used the null result to set a lower limit on how long a proton has to live, if it decays at all, through one specific channel, more than 8.2 times 10 to the 33rd power years. Through a second channel, more than 6.6 times 10 to the 33rd power years. Those are not measurements of lore. The proton has been proven to outlive that number, whatever its real lifetime turns out to be, and that number alone is already trillions of times older than the entire current age of the universe. That single, patient, so far completely negative result is the closest thing physics has to solid ground once you are standing this far out on the timeline. If protons are not perfectly eternal, on some almost incomprehensible schedule, ordinary matter itself eventually stops being able to hold its own shape. Push far enough past that, and even the objects that seemed the most permanent things this channel has ever covered are not exempt from the same arrow. The universe's darkest, densest structures are not frozen in place forever either. They too are subject to slow decline, on a schedule so long it dwarfs everything that came before it in this episode. Keep going, past every star, past every stellar remnant, past every last dense object, and you arrive at the destination atoms and Laughlin's framework is actually pointing toward. A 2013 paper by physicists Roxandra Bondarescu, Andrew Lundgren, and Mihai Bondarescu, describing this same far future. Cosmological horizon absorbs the contents of the universe, they wrote. The universe asymptotes towards an equilibrium state of the gravitational field, and flat space is the limit of that process, a state they describe as having divergent entropy. Strip away the technical phrasing, and here is what that means in plain language. Equilibrium. No more temperature differences to power anything. No stars converting one kind of energy into another. No chemistry, no structure, no motion that is not already as random as. Same disorder Boston University describes ticking upward in your kitchen, finally has nowhere left to increase, because it has already claimed everything there is to claim. That end state is what physicists mean when they say heat death. Not a bang. Not a rip, in this particular version of the story. A universe that has simply finished changing. Here is the part worth actually sitting with, because it is easy to hear all of this as bleak, and that reaction understates something. The same one-way arrow, the law that eventually flattens an entire universe into featureless equilibrium, is the exact same law responsible for absolutely everything interesting that has ever happened first. Stars only shine because they are moving toward higher entropy, releasing order as light. Chemistry only proceeds in one direction because of it. You, specifically, are a temporary, extremely improbable knot of low entropy, existing for a blink inside the early, generous part of this story, powered by a star that is still willing to burn instead of already having cooled. The same law that eventually quiets everything is the law that is currently paying for your existence. Nobody currently alive, and nobody who will ever be born, has any reason to plan around any of this. The nearer thresholds in this story alone are measured in numbers so large that human history does not even register as a rounding error against them. That is not a reason to look away from it. If anything, it is the opposite. You exist during the one era in this entire multi-part framework where existing is even possible at all, and depending on which of NASA's three scenarios turns out to be correct, that era is either a brief spark inside a universe that eventually goes calm and cold, or something else entirely, something nobody currently has enough evidence to rule out. So here is the honest question worth leaving in the comments. If the same law that guarantees a coffee goes cold also guarantees, eventually, on a timescale beyond real comprehension, that the entire universe goes quiet, does that make you want to know more about the exact number, or does the number stop being the point once it gets that large, and the fact that you are here to even ask about it becomes the actual story? In the next episode, we go looking in the opposite direction entirely. Instead of the very end, we go looking at the very beginning, and ask a stranger question than it sounds. Was the Big Bang actually the first thing that ever happened, or just the first thing we currently have any way of seeing? Somewhere in your kitchen, entropy just ticked up a little more while you watched this. So did the universes. Neither of them asked your permission, and neither of them ever will.